Hello everyone, it's great to be here with you today in this remote fashion and talk to you about the resource efficiency improving framework that we developed for deep reinforcement learning deployed on constrained devices. This work was done by my colleagues and I jointly between the UCL, the University of Oxford, and the University of Cambridge. Before we dive into the framework itself, let me talk briefly about deep reinforcement learning. We have an agent and an environment. The environment provides the agent with a state upon which the agent acts and receives a reward. This may come immediately after, but this reward at time t may actually be encoding the consequences of actions that were taken much further back in the past. What makes this deep reinforcement learning is that we use a deep model to fit the action value function on which on which the optimal actions are chosen. Our framework starts with an initial RL module and an environment that we're trying to optimize for. It uses a set of resource scalars that are identified based on the environment and on the module itself. The optimizer uses a greedy strategy with some regressional models that help guide it to the optimal decisions as to which of these to use to which degree. Our evaluation is split into two subsections. First, we look at simulated environments. On the right, we have the humanoid from OpenAI's robot school. Here, the objective is to teach a bipedal humanoid to walk. What we show is the memory profile our framework was able to deliver. We see that in the later stages of the RL modules training, the framework is requiring more memory than in the early ones, and this is reflective of the fact that in the later stages it can get away with such a strong compression as in the early ones. The most important parameter is the peak, which determines whether the agent can run on a specific piece of hardware. On the left hand side, we see the card pull from OpenAI's gym, where the objective is to move the base left and right such that the pole does not deviate more than 15 degrees off center. We see that our retention and conversely our compression is commensurate but still favorable relative to the reward loss. The second part of our evaluation is based on distributed coordination. The inputs to this are low-resolution images of moving objects, and each of these can be a car or not, can be red or not, and can have 2 wheels or 4 wheels. Our 5 agents are learning to jointly agree on communication protocol, use this to communicate gradients so that they learn from others' experience, not just their own, and then learn this simple classification task. All of them are deployed on separate ARM Cortex M0s. Our framework is capable of delivering considerable energy and latency savings while maintaining roughly the same performance as the baseline model. On the left-hand side, we see the energy and latency requirements of the baseline model, and then 65% and 35% retention cases. On the right-hand side, we see their performances. We see that while the energy falls considerably, the average reward over 100 episodes remains roughly the same. The framework therefore delivers optimized DQN models that are smaller, faster, require less energy, and retain roughly the same level of performance as the original models. Thank you for your attention.
for this one. I'd be actually curious on the second evaluation that you did, Philip. Is there with the distributed agents, with the M0 processors, can you give us an idea about the memory sizes involved for this distributed classification task?
I'll be honest with you, I don't remember these numbers from the head. I
just
remember very few things from
just order of magnitude or so.
a couple of megabytes.
Couple of megabytes. Okay, so it's not in the kilobytes; it's rather in the megabytes.
Yeah.
I think that helps already.
So that that was one of the feedbacks we received when we submitted this, and there was discussion between. So how small are these actually, and is it worth even trying to make them small? And my reaction to that would be that yeah, sure. I mean, and the task is relatively resource hungry. That is true. But this is a very good first step in the right direction. So like before we learn to walk, we can't run, right? So that is true.
Learning to walk, that brings me actually to the evaluation number 1.
Yeah.
There was a nice graph on the memory consumption peaking out at some point. Can you actually, is this upper bound, this peak memory consumption, is that deterministic? Can you guarantee a certain upper bound?
So that's estimate based on our experiments, and yeah, the peak is actually what you care about. In terms of theoretical guarantees of what can we deliver, we have not yet looked at that, but it is certainly on our list of to-dos.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Himax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML. Silicon Labs. Sentient. Google TensorFlow. XMOS. And lastly, silver sponsors, Edge Cortex, Hotchi, and Synsense.